Expanding Stargate to Michigan. More than 1 gigawatt campus to help build America's AI infrastructure and support economic growth in the Midwest. Today, we're announcing a new Stargate campus in Saline Township, Michigan, as part of our 4.5 gigawatts partnership with Oracle. Combined with capacity from our 6 previously announced U.S. Stargate sites with Oracle and SoftBank, this project brings Stargate to over 8 gigawatts of planned capacity and more than $450 billion in investment over the next 3 years, accelerating our progress and keeping us ahead of schedule to meet the $500 billion, 10-gigawatt commitment we announced in January. The infrastructure and manufacturing needed to advance AI give us a real chance to reindustrialize the country, and it should happen in places like Michigan. AI will unlock major benefits, from better healthcare to improved public services, and the build-out required to get there will generate significant opportunities along the way. We're investing through Stargate to help ensure communities across the country benefit both from building AI infrastructure and from all of the progress that AI itself makes possible. The Stargate Michigan campus is being developed by Related Digital, with construction expected to begin in early 2026, and will create more than 2,500 union construction jobs. The site will use a closed-loop cooling system that significantly reduces water consumption. DTE Energy will serve the campus using existing excess transmission capacity, avoiding impacts on local energy supply, and any upgrades required to support operations will be funded by the project and not local ratepayers. Across the U.S., Stargate sites are creating jobs, spurring investment in modern energy and industrial systems, and helping strengthen the supply chains needed to support the next generation of AI. Our expansion into Michigan builds on sites we've already announced in Texas, New Mexico, Wisconsin, and Ohio, each of which will help strengthen local economies and advance America's leadership in AI. Michigan has long been at the center of American engineering and manufacturing. We're proud to build here and to continue expanding the infrastructure needed to ensure the benefits of AI reach everyone. Introducing Aardvark, OpenAI's Agentic security researcher, now in private beta, an AI agent that thinks like a security researcher and scales to meet the demands of modern software. Today, we're announcing Aardvark, an agentic security researcher powered by GPT-5. Software security is one of the most critical and challenging frontiers in technology. Each year, tens of thousands of new vulnerabilities are discovered across enterprise and open-source code bases. Defenders face the daunting tasks of finding and patching vulnerabilities before their adversaries do. At OpenAI, we are working to tip that balance in favor of defenders. Aardvark represents a breakthrough in AI and security research, an autonomous agent that can help developers and security teams discover and fix security vulnerabilities at scale. Aardvark is now available in private beta to validate and refine its capabilities in the field. How Aardvark works. Aardvark continuously analyzes source code repositories to identify vulnerabilities, assess exploitability, prioritize severity, and propose targeted patches. Aardvark works by monitoring commits and changes to code bases, identifying vulnerabilities, how they might be exploited, and proposing fixes. Aardvark does not rely on traditional program analysis techniques like fuzzing or software composition analysis. Instead, it uses LLM-powered reasoning and tool use to understand code behavior and identify vulnerabilities. Aardvark looks for bugs as a human security researcher might, by reading code, analyzing it, writing and running tests, using tools, and more. Aardvark relies on a multi-stage pipeline to identify, explain, and fix vulnerabilities. Analysis. It begins by analyzing the full repository to produce a threat model reflecting its understanding of the project's security objectives and design. Commit scanning. It scans for vulnerabilities by inspecting commit-level changes against the entire repository and threat model as new code is committed. When a repository is first connected, Aardvark will scan its history to identify existing issues. Aardvark explains the vulnerabilities it finds step by step, annotating code for human review. Validation. Once Aardvark has identified a potential vulnerability, it will attempt to trigger it in an isolated, sandboxed environment to confirm its exploitability. Aardvark describes the steps taken to help ensure accurate, high-quality, and low false positive insights are returned to users. Patching. Aardvark integrates with OpenAI codecs to help fix the vulnerabilities it finds. It attaches a codex-generated and Aardvark scan patch to each finding for human review and efficient, one-click patching. Aardvark works alongside engineers, integrating with GitHub, codecs, and existing workflows to deliver clear, actionable insights without slowing development. While Aardvark is built for security, in our testing we've found that it can also uncover bugs such as logic flaws, incomplete fixes, and privacy issues. Real impact today. Aardvark has been in service for several months, running continuously across OpenAI's internal codebases and those of external alpha partners. Within OpenAI, it has surfaced meaningful vulnerabilities and contributed to OpenAI's defensive posture. Partners have highlighted the depth of its analysis, with Aardvark finding issues that occur only under complex conditions. In benchmark testing on golden repositories, Aardvark identified 92% of known and synthetically introduced vulnerabilities, demonstrating high recall and real-world effectiveness. Aardvark for open source. Aardvark has also been applied to open source projects, where it has discovered and we have responsibly disclosed numerous vulnerabilities, 10 of which have received common vulnerabilities and exposures, CV, identifiers. As beneficiaries of decades of open research and responsible disclosure, we're committed to giving back, contributing tools and findings that make the digital ecosystem safer for everyone. We plan to offer pro bono scanning to select non-commercial open source repositories to contribute to the security of the open source software ecosystem and supply chain. We recently updated our outbound coordinated disclosure policy, which takes a developer-friendly stance, focused on collaboration and scalable impact, rather than rigid disclosure timelines that can pressure developers. We anticipate tools like Aardvark will result in the discovery of increasing numbers of bugs and want to sustainably collaborate to achieve long-term resilience. Why it matters? Software is now the backbone of every industry, which means software vulnerabilities are a systemic risk to businesses, infrastructure, and society. Over 40,000 CVEs were reported in 2024 alone. Our testing shows that around 1.2% of commits introduce bugs, small changes that can have outsized consequences. Aardvark represents a new Defender-first model, an agentic security researcher that partners with teams by delivering continuous protection as code evolves. By catching vulnerabilities early, validating real-world exploitability, and offering clear fixes, Aardvark can strengthen security without slowing innovation. We believe in expanding access to security expertise. We're beginning with a private beta and will broaden availability as we learn. Private beta now open. We're inviting select partners to join the Aardvark private beta. Participants will gain early access and work directly with our team to refine detection accuracy, validation workflows, and reporting experience. We're looking to validate performance across a variety of environments. If your organization or open source project is interested in joining, you can apply here. How we built OWL, the new architecture behind our ChatGPT-based browser, Atlas. Inside our new process architecture, which gives you a faster, smarter way to use the web. By Ken Rocket, member of the technical staff, and Ben Goodger, head of engineering, ChatGPT Atlas. Last week, we launched ChatGPT Atlas, a new way to browse the web with ChatGPT by your side. In addition to being a full-featured web browser, Atlas offers a glimpse into the future, a world where you can bring ChatGPT with you across the internet to ask questions, make suggestions, and complete tasks for you. In this post, we unpack one of the most complex engineering aspects of the product, how we turn ChatGPT into a browser that gets more useful as you go. Making ChatGPT a true co-pilot for the web meant reimagining the entire architecture of a browser, separating Atlas from the Chromium runtime. This entailed developing a new way of integrating Chromium that allows us to deliver on our product goals. instant startup, responsiveness even as you open more tabs, and creating a strong foundation for agentic use cases. Shaping the foundation. Chromium was a natural building block. It provides a state-of-the-art web engine with a robust security model, established performance credentials, and peerless web compatibility. Furthermore, it's developed by a global community that continuously improves it. It's a common go-to for modern desktop web browsers. Rethinking the browser experience. Our talented design team had ambitious goals for our user experience, including rich animations and visual effects for features like Agent Mode. This required our engineering team to leverage the most modern native frameworks for our UI, SwiftUI, AppKit, and Metal, instead of simply reskinning the open-source Chromium UX. As a result, Atlas UI is a comprehensive rebuild of the entire application UX. We also had other product goals like fast startup times and supporting hundreds of tabs without penalizing performance. These goals were challenging to achieve with Chromium out of the box, which is opinionated about many details from the boot sequence, threading model, and tab models. We considered making substantial changes here, but we want to keep our set of patches against Chromium targeted so we could quickly integrate new versions. To ensure our development velocity was maximally accelerated, we needed to come up with a different way to integrate and drive the Chromium runtime. A litmus test for our technical investment was not only that it would enable faster experimentation, iteration, and delivery of new features, it would also enable us to maintain a core part of OpenAI's engineering culture, shipping on day one. Every new engineer makes and merges a small change in the afternoon of their first day. We needed to make sure this was possible, even though Chromium can take hours to check out and build. Our solution, OWL. Our answer to these challenges was to build a new architectural layer we call OWL, OpenAI's web layer. OWL is our integration of Chromium, which entails running Chromium's browser process outside of the main Atlas app process. Think of it like this. Chromium revolutionized browsers by moving tabs into separate processes. We're taking that idea further by moving Chromium itself out of the main application process and into an isolated service layer. This shift unlocks a cascade of benefits. A simpler, modern app. Atlas is built almost entirely in SwiftUI and AppKit. One language, one tech stack, one clean code base. Faster startup. Chromium boots asynchronously in the background. Atlas doesn't wait. Pixels hit the screen nearly instantly. Isolation from jank and crashes. Chromium is a powerful and complex web engine. If its main thread hangs, Atlas doesn't. If it crashes, Atlas stays up. Fewer merge headaches, because we're not building on as much of the Chromium open source UI. Our diff against upstream Chromium is much smaller and easier to maintain. Faster iteration. Most engineers never need to build Chromium locally. OWL ships internally as a pre-built binary, so Atlas builds take minutes, not hours. Because most engineers on our team aren't regularly building Chromium from source, development can go much faster. Even new team members can merge simple changes on their first afternoon. How OWL works. At a high level, the Atlas browser is the OWL client, and the Chromium browser process is the OWL host. They communicate over IPC, specifically Mojo, Chromium's own message passing system. We wrote custom Swift and even TypeScript bindings for Mojo, so our Swift app can call host-side interfaces directly. The OWL client library exposes a simple public Swift API, which abstracts several key concepts exposed by the host service layer. Session. Configure and control the host globally. Profile. Manage browser state for a specific user profile. Web view. Control and embed individual web contents, e.g. render, input, navigate, zoom, etc. Web content renderer. Forward input events into Chromium's rendering pipeline and receive feedback from the renderer. Layer host/client. Exchange compositing information between the UI and Chromium. There's also a wide range of service endpoints for managing high-level features like bookmarks, downloads, extensions, and autofill. Rendering, getting pixels across the process boundary. Web views, which share a mutually exclusive presentation space in the client app, are swapped in and out of a shared compositing container. For example, a browser window often has a single shared container visible, and selecting a tab in the tab strip swaps that tab's web view into the container. On the Chromium side, this container corresponds to a GFX, accelerated widget, which is ultimately backed by a Kali layer. We expose that layer's context ID to the client, where an NS view embeds it using the private Host API. Special cases like select drop-downs or color pickers, which Chromium renders in separate pop-up widgets, use the same approach. They don't have a content, web contents, but they do have a content, render widget host view with their own GFX, accelerated widget, so the same delegated rendering model applies. OWL internally keeps view geometry in sync with the Chromium side, so the GPU compositor can be updated accordingly and can always produce layer content to the correct size and device scale. We also reuse this technique to selectively project elements of Chromium's own native views UI into Atlas. This is also useful for bootstrapping features, like permission prompts quickly without building replacements from scratch in SwiftUI. This technique borrows heavily from Chromium's existing infrastructure for installable web apps on macOS. Input events, cracking, and forwarding. Chromium UI translates platform events, like macOS and S events, into Blink's web input event model before forwarding them to renderers. But since OWL runs Chromium in a hidden process, we do that translation ourselves within the Swift client library and forward already translated events down to Chromium. From there, they follow the same lifecycle that real input events would normally follow for web content. This includes having events return back to the client whenever a page indicates that it didn't handle the event. When this happens, we re-synthesize an NS event and give the rest of the app a chance to handle the input. Agent mode, special cases. Atlas Agentic browsing feature poses some unique challenges for our approaches to rendering, input event forwarding, and data storage. Our computer use model expects a single image of the screen as input, but some UI elements like select dropdowns render outside the tab's bounds in separate windows. In agent mode, we composite those pop-ups back into the main page image at the correct coordinates, so the model sees the full context in one frame. For input, we apply the same principle. Agent-generated events are routed directly to the renderer, never through the privileged browser layer. That preserves the sandbox boundary even under automated control. For example, we don't want this class of events to synthesize keyboard shortcuts that make the browser do things unrelated to the web content being shown. Agent browsing can also run in an ephemeral, logged-out context. Instead of sharing the user's existing incognito profile, which could leak state, we use Chromium's storage partition infrastructure to spin up isolated in-memory stores. Each agent session starts fresh, and when it ends, all cookies and site data are discarded. You can run multiple logged-out agent sessions, each one in its own browser tab, and each fully isolated from the others. A new way to use the web. None of this would be possible without the global Chromium community and their incredible work building a foundation for the modern web. OWL builds on that foundation in a new way, decoupling the engine from the app, blending a world-class web platform with modern native frameworks, and unlocking a faster, more flexible architecture. By rethinking how a browser holds Chromium, we're creating space for new kinds of experiences. Smoother startups, richer UI, tighter integration with the rest of the OS, and a development loop that moves at the speed of ideas. If that sounds like your kind of challenge, check out our openings to work on Atlas as a software engineer, Atlas, software engineer, iOS, and more. Introducing GPT-OSS Safeguard. New open safety reasoning models, 120B and 20B, that support custom safety policies. Today, we're releasing a research preview of GPT-OSS Safeguard, our open-weight reasoning models for safety classification tasks, available in two sizes, GPT-OSS Safeguard 120B and GPT-OSS Safeguard 20B. These models are fine-tuned versions of our GPT-OSS open models and available under the same permissive Apache 2.0 license. allowing anyone to use, modify, and deploy them freely. Both models can be downloaded today from Hugging Face. The GPT-OSS Safeguard models use reasoning to directly interpret a developer-provided policy at inference time, classifying user messages, completions, and full chats according to the developer's needs. The developer always decides what policy to use, so responses are more relevant and tailored to the developer's use case. The model uses chain of thought, which the developer can review to understand how the model is reaching its decisions. Additionally, the policy is provided during inference rather than being trained into the model, so it is easy for developers to iteratively revise policies to increase performance. This approach, which we initially developed for internal use, is significantly more flexible than the traditional method of training a classifier to indirectly infer a decision boundary from a large number of labeled examples. GPT-OSS Safeguard enables developers to draw the policy lines that best fit their use case. For instance, a video gaming discussion forum might want to develop a policy to classify posts that discuss cheating in the game, or a product review site might want to use its own policy to screen reviews that appear likely to be fake. The model takes two inputs at once, a policy and the content to classify under that policy, and outputs a conclusion about where the content falls, along with its reasoning. Developers decide how, if at all, to use those conclusions in their own safety pipelines. We've seen this reasoning-based approach perform especially well in situations where the potential harm is emerging or evolving, and policies need to adapt quickly. The domain is highly nuanced and difficult for smaller classifiers to handle. Developers don't have enough samples to train a high-quality classifier for each risk on their platform. Latency is less important than producing high-quality, explainable labels. We're releasing this preview of GPT-OSS Safeguard to receive feedback from the research and safety community and iterate further on model performance. Over months, we worked on this open-weight release with Roost to identify developers' critical needs, test the model, and produce developer documentation. As part of this launch, Roost will be establishing a model community, also launching today, to explore OpenAI models to protect online spaces. Alongside this release, we're publishing a short technical report that details the safety performance of this preview model. System-level safety, the role of safety classifiers. When it comes to safety, we believe in defense in depth. We train our models to respond safely, and we implement additional layers of protection to detect and address potentially unsafe inputs and outputs under our policies. Safety classifiers, which distinguish safe from unsafe content in a particular risk area, have long been a primary layer of defense for our own and other large language models. Traditional safety classifiers, such as those available via our moderation API, are developed by manually curating thousands of examples of safe and unsafe content under predefined safety policies. From this training data, the classifier learns to distinguish safe from unsafe outputs. In this traditional approach, the classifier never actually sees the safety policy. Instead, it attempts to infer the underlying policy that was used to label the examples by finding similarities in the content labeled as unsafe and differences between the unsafe and safe content. Traditional classifiers can have high performance, with low latency and operating cost. But gathering a sufficient quantity of training examples can be time-consuming and costly, and updating or changing the policy requires retraining the classifier. GPT-OSS Safeguard is different because its reasoning capabilities allow developers to apply any policy, including ones they write themselves or draw from other sources, and reasoning helps the models generalize over newly written policies. Beyond safety policies, GPT-OSS Safeguard can be used to label content in other ways that are important to specific products and platforms. How we use safety reasoning internally. Our primary reasoning models now learn our safety policies directly and use their reasoning capabilities to reason about what's safe. This approach, which we call deliberative alignment, significantly improves on earlier safety training methods and makes our reasoning models safer on several axes than their non-reasoning predecessors, even as their capabilities increase. But reasoning isn't only useful for training the models themselves. It also creates new possibilities for defense and depth. Reasoning-based approaches are more flexible and less limited by the details of their previous training, advantages that sometimes more than justify the additional compute cost and latency they involve. GPT-OSS Safeguard is an open-weight implementation of an approach we developed internally in a tool we call Safety Reasoner. We began with reinforcement fine-tuning on policy labeling tasks, rewarding the model for mirroring correct judgments from human experts. This taught the model to reason about how the policy leads to its judgment. Today, Safety Reasoner enables us to dynamically update our safety policies in production in less time than it would take to retrain a classifier. This makes Safety Reasoner a key tool for iterative deployment. When we deploy new models to production, we often start with more strict policies and use relatively large amounts of compute where needed to enable Safety Reasoner to carefully apply those policies. Then we adjust our policies as our understanding of the risks in production improves. In some of our recent launches, the fraction of total compute devoted to safety reasoning has ranged as high as 16%. Safety Reasoner has become a core component of our safety stack. For image generation and Sora 2, it performs dynamic, stepwise evaluations of outputs to identify and block unsafe generations in real time. In domains such as biology and self-harm, we run models like those used in the Moderation API as small, fast, and high-recall classifiers to determine which content is within a domain of interest, and then use Safety Reasoner to review that content. Safety Reasoner classifies model outputs against a detailed taxonomy to determine how best to respond, forming part of our multi-layered safeguard across systems like GPT-5 and ChatGPT Agent. And now, the GPT-OSS Safeguard models make this same approach available to anyone. How GPT-OSS Safeguard performs. We evaluated the GPT-OSS Safeguard models on both internal and external evaluation sets. In the internal evaluation, we provided multiple policies simultaneously to GPT-OSS Safeguard at inference time. For each test input, we evaluate whether GPT-OSS Safeguard correctly classifies the text under all of the included policies. This is a challenging task. The model is counted as accurate only if it exactly matches the golden set labels for all the included policies. Our GPT-OSS Safeguard models and internal Safety Reasoner outperform GPT-5 thinking and the GPT-OSS Open models on multi-policy accuracy. The GPT-OSS Safeguard models outperforming GPT-5 thinking is especially surprising given the former model's small size. We further evaluated these models on the moderation dataset we released with our 2022 research paper and on Toxic Chat, a public benchmark based on user queries to an open-source chatbot. On the 2022 moderation evaluation set, we evaluated using our internal safety policies, adapting one policy to account for subsequent changes. GPT-OSS Safeguard slightly outperformed all other tested models, including our internal Safety Reasoner and GPT-5 thinking, though this difference between Safety Reasoner and GPT-OSS Safeguard is not statistically significant. For Toxic Chat, we evaluated using a short handwritten prompt adapted from some of our internal policies. Our internal Safety Reasoner again outperformed GPT-5 thinking, while GPT-5 thinking and Safety Reasoner both marginally outperformed GPT-OSS Safeguard 120B and GPT-OSS Safeguard 20B. We expect that the relatively small size of GPT-OSS Safeguard still makes it preferable for this type of task. Limitations. There are two specific limitations of GPT-OSS Safeguard. First, we have observed that classifiers trained on tens of thousands of high-quality labeled samples can still perform better at classifying content than GPT-OSS Safeguard does when reasoning directly from the policy. Taking the time to train a dedicated classifier may be preferred for higher performance on more complex risks. Second, GPT-OSS Safeguard can be time and compute intensive, which makes it challenging to scale across all platform content. Internally, we handle this in several ways with Safety Reasoner. 1. We use smaller and faster classifiers to determine which content to assess, and 2. In some circumstances, we use Safety Reasoner asynchronously to provide a low-latency user experience while maintaining the ability to intervene if we detect unsafe content. The road ahead, continuing to build with the community. GPT-OSS Safeguard is OpenAI's first set of open safety models built with the community. We've iterated on GPT-OSS Safeguard with trust and safety specialists at SafetyKit, Roost, Tomorrow, and Discord as part of early testing. Roost CTO Vinay Rao says, GPT-OSS Safeguard is the first open-source reasoning model with a bring-your-own policies and definitions of harm design. Organizations deserve to freely study, modify, and use critical safety technologies and be able to innovate. In our testing, it was skillful at understanding different policies, explaining its reasoning, and showing nuance in applying the policies, which we believe will be beneficial to builders and safety teams. We'll continue to iterate with the community to improve open safety tooling, including through the Roost Model Community, RMC. The RMC brings together safety practitioners and researchers to share best practices for implementing open-source AI models into safety workflows, including evaluation outcomes and model feedback. Visit the RMC GitHub repo to learn more about this partnership and how to get involved. To start building with these models, download them from Hugging Face. Technical Report: Performance and Baseline Evaluations of GPT-OSS Safeguard 120B and GPT-OSS Safeguard 20B. Introduction: GPT-OSS Safeguard 120B and GPT-OSS Safeguard 20B are two open-weight reasoning models post-trained from the GPT-OSS models and trained to reason from a provided policy in order to label content under that policy. They are available under the Apache 2.0 license and our GPT-OSS usage policy. Developed with feedback from the open-source community, these text-only models are compatible with our Responses API. The models are customizable, provide full chain of thought, can be used with different reasoning efforts, low, medium, high, and support structured outputs. In this report, we describe GPT-OSS Safeguard's capabilities and provide our baseline safety evaluations on the GPT-OSS Safeguard models, using the underlying GPT-OSS models as a baseline. For more information about the development and architecture of the underlying GPT-OSS models, see the original GPT-OSS model card. We recommend using these models to classify content against a provided policy, and not as the core functionality with which end users interact. The original GPT-OSS models are better for those applications. The safety metrics provided below describe how GPT-OSS Safeguard models function in chat settings. The GPT-OSS Safeguard models are not intended for this use, but since they are open models, it is possible for someone to use the models in this way. Because of that possibility, we wanted to verify that they met our safety standards in such usage. This report shares the results of those tests. We also share an initial evaluation of multi-language performance in a chat setting. Note that this does not directly assess performance during content classification with a provided policy. The GPT-OSS Safeguard models are fine-tunes of their GPT-OSS counterparts and were trained without any additional biological or cybersecurity data. As a result, we determined that the previous work estimating worst-case scenarios from GPT-OSS release cross-applies to these new models.